Yeah, hi everyone. You can check out the upcoming data sessions. The link for them is given in the chat section. And please stay tuned. We'll be starting in few minutes. Hello and welcome everyone to the another session of the data series. We'll start in 5 minutes. Till then, let's get to know each other. So we have put up a poll which contains two questions. So kindly fill in the poll. Hello everyone. Uh, so we'll start in just 2-3 minutes. Till then, please stay tuned. And Okay. Hello and welcome everyone to another session in the DataHour series. We are thrilled to be here with you this evening for a session full of action-packed learning. I am Rishabh Kumbhalkar, part of the data science team at Analytics Vidhya, and I'll be the moderator for this session. For those who have joined us for the first time, a brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding for our community members. Now, on to our session today, which is about dynamic time warping for time series classification. In time series analysis, dynamic time warping is an algorithm for measuring similarity between two sequences, which may vary in time or speed. In this data, the use of dynamic time warping as feature embedding and dynamic time warping as metric will be discussed in details. So I hope you guys are excited to attend this data with us. But before we kick things off and I hand it over to our speaker, a quick recap of housekeeping items. We are recording this session and we'll make the recording available on our YouTube channel in few days. Please use the question and answer section, Q&A section, for asking any questions you might have during the session, and we'll do our best to answer them as the data progresses or towards the end. Also, we have shared an introductory poll with you guys, so I hope you have filled it in. And also we'll be sharing another poll about the feedback of this session towards the end, which I request you to kindly fill up. And now on to our speaker. In this session of DataHour, we have Sumit Lalla with us. Sumit has done Masters of Data Science from Higher School of Economics, Moscow, and Bachelors of Engineering in Computer Engineering from Thapar University. He has over 5.5 years of experience in data science and software engineering. Sumit is currently working as a data scientist in Cognizant and have previously worked as a software developer in Siemens Technology and Services and technology analyst in Deloitte Consulting and Private Limited. Over to you, Sumit. The virtual stage is all yours.
Thank you, Rishabh. Good afternoon and good morning to all. I will share my screen. Let me know once it's visible.
Yeah, so it is visible.
Thank you, Rishabh. Yeah, so we would be discussing on the time series spectral image data, and we would be using ML-based classification approach. So basically, it was a agriculture time series spectral image data. So we would be proceeding to the next slide. So given the background of the topic, our objective was to predict the growth of wheat crop in a given geographical area in various districts in India. And the satellite data was available from October to May 2020-2021, and it was provided by a startup company. And due to some client constraints, the NDVI, the normalized difference vegetation index, was pre-computed from it, and that input was shared to us by the startup company. So going on to this metric, normalized difference vegetation index, it basically has its values from -1 to +1. So it is calculated using the IR and the NIR range of the light. So if we have -1, that means that the cropland is barren, and +1 means that the cropland has a crop grown on it or some type of vegetation is there. So more on it, I can share the material. And the time series data was given for the Ndvi data. So it had unequal length and there were different starting and ending points with different velocity and different or similar phase shifts. So by different starting and ending points, we mean that some of the crop period have the timeline from 1st October till the end of May. For some of the crops, it was starting from 1st November to April. And with different velocities, we mean that there were some spikes in the time series, and it was sometimes discontinuous for the starting and ending points. But one thing to note here was that between the time intervals, the data wasn't missing. So we had a continuous data in between. Only from the start and ending points, the data wasn't there because of the different starting and ending periods of the crop growth. So these all points made us use the dynamic time warping concepts. So we will study more of this on to the next slides. And here actually we have done a study on the NAVE implementation of it as well as the optimized and the more suitable implementation for it for this given data. So here, as we have seen, we have the time series with different or similar phase shifts. So for the optimized approach, we will discuss in the upcoming slides. And these type of methods can be used in various facets of agriculture, like we can determine whether the land is arable or barren, and we can also classify the land cover mapping of the forests or the crop mapping. And there are many other topics which can be handled by this concept. And we are studying the two approaches. One is we are using dynamic time warping as a metric, and then dynamic time warping as feature embeddings. And then we will compare its results. So let us proceed to the data for this problem. So we had the phenological information of the area. So this was for one district in Haryana, Karnal. So we had the Ndvi time series values. So one person, I think, have posted a question, what is time series? So basically we have the y values and the x values, and the x values corresponding to certain time period, and the Ndvi values are the time series values for this. So this is basically the seasonal trend of the data for the given period of time. So in our case, we are focusing on time series, but we are more interested onto the structural properties of the time series signals. So for the missing data from the starting and ending point, we haven't accounted for the missing values. Like we are not predicting the missing values that they should be following some pattern, because that could have introduced bias in our data sets. So this type of thing also dynamic time warping handles quite well. And coming to the other set, we have the geographical information of the area. So we have the lat long of the district, and the area has the corresponding region ID. So for different region IDs, there are the wheat values, whether the wheat is grown or not on that region. And we have different lat long values, which can be used as a feature in the ML-based classification. So one question is there, what happens if data is missing in between data gaps? If data is missing, then we have to apply some interpolation to predict the values, because then we will have discontinuous data and we won't be able to solve the DTW metric efficiently, because here we require the continuous flow of data. So actually we can apply the LOESS interpolation for predicting the missing data, and we can apply some smoothing operations on our time series. So for that, actually, then we can proceed with the ARIMA and these SARIMAX based methods for time series forecasting. And then we can apply the DTW. Yeah, Mayur, you're right. Like interpolation, we can't do for this problem because bias will be introduced. But if if we have discontinuous data, then we have to do some time series forecasting in between and then use this method. Okay, you're welcome. Now coming to dynamic time warping naive implementation. So basically dynamic time warping is based on edit distance string algorithm. So we are taking two subsequences. Ndvi was given from the startup actually. Like this data was already pre-computed. I hope this answers, Shailendra. And for pre-processing, actually, we analyzed the signal structure and we got that the signal structure was continuous. There were no discontinuities in between. There were different starting and ending points of the signal. So we zeroed down upon this approach. I hope this answers the pre-processing question. Yeah, Priyanshu, you can tell the question. Hello, Priyanshu.
Yeah, I guess he has put down his hand.
Okay.
Priyanshu, you can post your question.
Okay, coming to the dynamic time warping algorithm. So it basically follows the string edit distance algorithm between the two subsequences. So subsequences here are the time series for the two regions for the given district. So we would be considering all these subsequences using dynamic programming, and we will consider all possible alignments as we see in the string, like when we are inserting, deleting, or substituting a character when we are matching the two strings. And the distance we would be using would be like it would be a p norm. It would be either like 1 norm, 2 norm. So in this case, I have used 1 norm Manhattan distance. And then the penalty, which involves the insertion, deletion, or matching of the subsequences, are computed by solving the subproblem. And as we know, the algorithm of the edit distance, we can either solve it recursively or using dynamic programming. So dynamic programming is faster and it takes less memory. So we would be doing dynamic programming and caching the results and Then we would be adding the distance and the penalty to get the subproblem result, and that we would be storing in the cost matrix. Yeah, Subhash, I will take this question at the end actually. So we would be getting the final value of the dynamic time warping, which will be the topmost right corner of the cost matrix. So that will be the final dynamic time warping value, and it will denote that how much insertions, deletions, and substitutions we need so that the time series of one region ID can match with another region ID. Okay, I will take the questions at the end. So this is the cost matrix, and as we see here, actually the alignment is bit staggered and it is wavered across the diagonal. So the optimum will be when we have the diagonal at 45 degrees of the cost matrix. So we would see in the next slides that our optimum approach will give this scenario. So now we see the optimal alignment plot. We here see that we have some points on the plot, so they have two alignments in between. So there are multiple alignments also. So this is for the naive approach. Actually, we say that the alignment is not single. Actually, there is no single linkage between all the points for the time series. So the path can be traced from the cost matrix by taking a traceback matrix, and then we can increment decrement in indices, and the indices of the time series can be appended to the path list, and then we can reverse the path list because we have started from the end position to get the path from the starting position. And then we would require the traceback matrix also to store the minimum penalty that will be used when to calculate the path from the starting to the end position. So this also we will see that there would be single linkage when we use optimum approach. So coming to the optimum approach, so in the starting we had seen that the time series had similar or horizontal phase shifts. So for that actually we would be introducing a weighted cost penalty function. So either we can introduce linear one or logistic one. So for this use case, logistic one gave a better accuracy. So for this, we used the logistic weighted cost penalty function. So logistic weighted cost penalty function takes two hyperparameters, alpha and beta. So alpha denotes the steepness of the logistic curve, and the beta denotes the midpoint of the logistic curve, and that is the difference in the number of days between the two time series. So for that, actually, we have to tune this hyperparameter to get the alpha and beta for our data. So we had to do some experiments on the data to get over the alpha and beta value. So either you can do cross validation, or if you have domain knowledge, then you can estimate the value of alpha and beta. So this logistic weight function will be calculated, and this will be added to the dynamic time warping algorithm while calculating the cost. And now we see actually the time warping cost matrix has a sort of perfect diagonal when we are doing the alignment. So we have it at around 45 degrees. No, though it is not perfect, but still we can tune it by appropriately selecting the alpha and beta. And the second plot shows that the linkage between the 2 points for the time series. So note that actually we had double linkage for the points on the time series. Now we have a single linkage, and it gives much better result than the naive method. And this we will see when we are applying classification methods while predicting the wheat growth. So coming to the technology stack, we have used Python, NumPy, Pandas, Colab for CPU, GPU support, and Numba for calculating the cost matrix, and it has the just-in-time compiler, so it translates the Python and NumPy code into fast machine code, and this was helpful when we were estimating the hyperparameters. And we are using Optuna. It is a hyperparameter tuning framework, and it uses Bayesian optimization by default, and it is a wonderful library, and we can predict quite efficiently, and it is faster than grid search CV and randomized CV. And then we use scikit-learn to predict the evaluation metrics and to get the classification reports, and for some basic machine learning algorithms like support vector classifier and random forest classifier. So coming to methodology, we are preparing the training and test data by splitting it into 75% and 25% using stratified k-fold cross-validation. And we had the latitude and longitude data. So we are converting it to normalized spherical coordinates. And then we are concatenating it with the DTW feature embeddings. And so actually DTW feature embeddings are calculated similarly when we consider two subsequences. So one would be the training subsequence, one would be the validation subsequence for calculating the feature embeddings for the validation set. For the training set, we would have two subsequences of the training set. So in that way, we are calculating the feature embeddings, and dimensionality, actually, it will have high dimensionality, but we can reduce the dimensionality by using Laplacian eigenmap. But results are somewhat similar only because this is not exactly a distance metric, and various considerations are involved when we are calculating the alignment. And there are some limitations of using Numba library while calculating the DTW cost, because we have some complex data types like date time that are not supported by Numba. So we have to convert it into seconds, and then we have to do some computations to get over it. And there are some complex functions like min max, though it not that much complex, but still Numba doesn't handle those. So for those implementations, we have to do our own implementation. But this library actually will reduce the computation cost. Like for us, actually, it reduced around 60 times. So it was quite helpful in this situation. And also DTW, we are using not the faster version, actually. The faster version will have the lower bounds and all considerations, and we would stop in between to get the approximate lower bound for DTW. Here we are running it for the full matrix. So it will take like around OMN time complexity. So that for that also we need high performance computing. And we can also do parallel computing of DTW, but currently it is single processing only. So coming to methodology, we discussed that we would be using DTW as a metric and DTW as a feature embedding. So DTW as a metric, we can use it with 1NN. So 1NN actually is implemented in sklearn. Either you can use that implementation and use the DTW as a metric, or you can do a custom implementation of 1NN. And then we can compute the alpha and beta hyperparameters that we discussed in the previous slides. And this was computed because 1NN based method was comparatively more efficient than DTW as feature embedding. So we calculated alpha and beta using this, and it was treated on similar train and test data set. And then we compute the metric for test set. with respect to the training set. And here we considered individual districts as well as merged districts to see how the performance of the individual model is there on the merged data or individual data, as well as the merged model on the individual data. So we would see the results on the subsequent slides. And in case of tie for the value of DTW metric between the two records, we are considering the majority voting algorithm. So we are considering that record which had come earlier. So then we are comparing the test set results for both the naive approach as well as the optimized approach. So then coming to DTWS feature embeddings, as discussed earlier, we are creating feature embedding matrix using the DTW algorithm by taking two subsequences for training and test data set. And test data set we would be creating with respect to the training set. So then we are using the SVC and random forest classifiers for building the model on the naive and optimized DTW embeddings for the individual data as well as merged data. And then we are performing hyperparameter tuning on the above classifier models using Optuna, and we are also using inner stratified k-fold cross-validation to avoid overfitting for them. And then we are comparing the test results for the naive approach as well as optimized approach for the above classifiers. So as we see here in 1NN naive DTW individual model, we have for Dtws actually we see the evaluation metrics are not that much good. And if we go to the next slide, we have the 1NN time weighted DTW individual model. So we can see here actually the metrics have somewhat improved. And for merged data, actually it will perform worse because we have trained it on individual data set. So coming to 1NN DTW merged model. So we are trying to predict on individual data. So it will not give that much good results, and it will give results that have bias because we already have some of the data from the districts, and test data set also includes some data. So we are getting these results, and this we would see like how it is thrown away. This assumption is thrown away when we use the optimized approach. Yes, Rahul, you had a question.
Rahul, you can put in the Q&A section the query. Thank you. Yes, Sonu, please continue.
Sure. So coming to 1NN time weighted DTW merge model, same actually. The data was there. So because the common data is there, so we are getting all these results, which we would see in other classification methods, how this performance will not be that good due to less number of observations in test set. And coming to SVC naive DTW individual model. So the results are improved from the 1NN naive DTW individual model. So it gives a hint that feature embedding using DTW as a feature embedding is better than the DTW when using 1NN as a metric. And the results we can see, but here we can see Cathal, the AUC has decreased, and overall value of the metrics is also not good because Cathal less number of observations are there and number of features are quite more. So our model is learning noise and it is overfitting. Same if we go for SVC time weighted DTW individual model. So here we can see actually Cathal actually it has improved quite much, and we see these are the best results actually which we obtained from the optimized approach. So we have got comparative results. Though data is less in Cathal, we are getting good AUC. Same if we compare SVC naive DTW merged model. So here we would have large number of features. So and the number of observations are quite less in Cathal, so that AUC drastically reduces. So this gives us a hint that naive model performs quite worse than the optimized model. Coming to SVC time-weighted DTW merged model, we see actually here cattle actually it is performing worse as the number of observations are less, and Karnal and Dtws it is comparable to the previous results. And then we also applied random forest classifier on this naive DTW model. So we got these results, but these results were not that much good as we got from the support vector classifier model. And similarly, we can see for time weighted DTW, RFC. And here also RFC naive DTW merged model. For cattle, we have relatively less score on this AUC, and also recall precision, everything is not good. Just like we saw for the SVC, the reasons are similar, and RFC time weighted DTW merged model also same thing. So we got the best results through the SVC time weighted DTW individual model, and it's better to use the individual model rather than the merged model. So from the results we can see, based on the alpha and beta, which were calculated by doing certain experiments on this individual district data. So as we see the results, actually, when DTW as a metric can be used when we have to estimate the alpha and beta hyperparameters for the optimized DTW or the time weighted DTW. And it is also easy to explore, and we can implement the 1NN ourselves, and that alpha and beta can be used for the second method, that is the DTW as feature embeddings. And as we saw in the merged model, the performance decreased when the number of features were greater than the number of observations. So this is independent of this. And so when we have this scenario, then we can use 1NN time weighted model for classifying. And this model performance was not good on the individual test set when we compare it with the feature embeddings calculations, and that we saw prior. And DTWS feature embeddings we can use for the individual model, as we will have the number of observations greater than number of features, and as we saw that the performance degrades when the features is greater than number of observations. And here we saw that SVC is performing better on Kethel and Karnal, though there was some less number of observations and high dimensionality of the features. So SVC tends to perform better on high dimensionality of features. We could have done dimensionality reduction using Laplacian eigenmap, but they give comparative results. So it's fine actually that we can use this for higher dimensional embeddings. And so we can conclude the results by saying that we can use DTW as a metric with 1NN for faster computation of alpha beta hyperparameters that can be used for the second approach when we are using DTW as feature embeddings. And we should use DTW as a metric with 1NN classification when we have the number of observations less than the number of features. And we can use 1NN classification with DTW as a metric, and we can define a baseline model, and we can compare the results with the second method, which we would be using for further use cases. And DTW as feature embeddings can be used on the individual data. So in the individual data, we will have number of observations greater than number of features. And we can use DTW as a feature embedding to get better evaluation results on the individual model, and the hyperparameters can be derived from the first approach. And coming to future work, we would be extending DTW as feature embeddings to learn it and through the neural network architectures and deep learning classification techniques. And we would be enhancing the evaluation metrics further by concatenating SAX encoders with the feature embeddings. And there was one point that the computational cost is around OMN. So that thing actually can be reduced either through the lower bound, or we can use faster approaches by using triangular global alignment kernels on the given data set. And this can be correlated with the SVC. So yeah, thank you all actually. If we can walk through the code if people are willing to, or the floor is open for questions.
Yeah, you guys can let us know in the chat section. Yeah, okay. Yeah, Sumit, we have some time as well.
Sure.
If you can, we can walk through the code.
Sure, I will share my screen once.
Yeah.
Yeah, let me know once my screen is visible.
Yeah, it is visible.
Okay. Okay, so coming to the pre-processing part, actually the data wasn't in the format which I shown you. So we had to do certain things before computing it. So like we were converting it to a group data frame of seasonal dates. So basically we have the date time as an index, and we have the region IDs as the columns. So we had individual values for the given date time for all the region IDs. So for that, we are pre-processing the district data. And so then for clustering, actually, we are using HDB scan. So HDB scan, we are using the Earth's radius, that is 6,400, and then we are calculating the epsilon value, which will be 1.5 upon the Earth radius. And then we are segregating the latitude and longitude into clusters. And for that, actually, we are doing it based on the relative validity index, that is the DB index for the HDB scan. So based on the best clustering, we are using those cluster labels, and that we are appending it to the pre-processed data and storing it in separate file. This method is for generating the merged data for all the districts. So for that, actually, we had Devas, Karnal, and Kaithal districts. So that we are doing random sampling, and then we are combining them, and then we are splitting it into train and test using train test split into 75 and 25. Then some more pre-processing is done. Similarly for Karnal, Kaithal, it's done. Then for individual model also, we are using the same pre-processing. And then we are creating the Ndvi time series for the district data. So the data which we have pre-processed from the above we are using, and we are creating the dictionary using the date time and the Ndvi values. So for that, actually some processing operations are done, and we have just missing values in start and end. So we have to check for none values, and based on that, we would create the dictionary. And same thing we have done for the merged data. So the code actually needs some refactoring. And after making those dictionaries, we are storing it in NPI file for further processing. So here actually we are using the dynamic time warping algorithm. So it's based on the string edit distance algorithm, and the traceback matrix we saw in the slide. This we are using for getting the path from the end to the start point, and this is the optimized approach. So we are using the penalty function. And here we can set the hyperparameters based on some experiment. The experiments were done in another notebook. So and for number actually, then we can import the JIT, and JIT we can give the function name, and no Python is if we give no Python is equal to false, it will treat it as a Python code, and it will run in relate. It will take more time actually, because it won't translate it into machine level code. Then we are using the 1NN based implementation. So for 1NN, we have done a custom implementation, and here we are using the distance function, and we had all the dictionaries set up previously. So that part we are using an alpha beta we had calculated from the experiments. We would be generating the classification report and storing the model and storing the report in the file. This is for generating the spherical coordinates for the latitude and longitude. We can visualize the time series plots also. So this mostly we are checking the alignment also. This we saw in the slide, so we can do by this method. And for using dynamic time warping as a feature embedding, this is a very high performance compute. So we had to use Numba, and also the this we have taken it as symmetric, that for DTW between 1 and 2 will be same as DTW between 2 and 1, and DTW between two same subsequences will be 0. And then we are generating the training feature embedding matrix. So we are using a combination, because we need one training sample, and one we would have the second subsequence, which will be also the training. So we can do it by using combinations, and training it will be same only. So that we can take it as 0. Same thing we have done. And then we are using the latitude and longitude, same thing actually. We are doing feature engineering here. We are concatenating this with the feature embeddings, the spherical coordinates. And we are using hyperparameter tuning using Optuna. And for that, actually, we are doing it for the support vector classifier and for random forest classifier. And inner cross validation we are using to reduce the chances of overfitting. And if there are some errors, we can raise it in the cross-val score using the error score raise. And then we are creating the study, and we have to maximize the AUC metric. So we are using direction is equal to maximize. If it would have been lost, we could have used the minus sign. So maximize will be reduced to minimize. And some ranges of hyperparameter values are given. Same for random forest classifier. We are setting up the range for some of the hyperparameters, and then we are using inner cross stratified k-fold cross validation, and we are optimizing our AUC metric. Then we are evaluating the results on the test set. So yeah, and then we are storing the support vector classifier model and random forest classifier model. So actually the code is in nascent stage. Actually, some refactoring is required, and I'm planning to push it to PyPy repository. So anyone who is willing to work with me can work. So basically, I'm trying to make DTW as a metric and feature embeddings as a Python package. And currently the time weighted part is implemented in R. So this we can do it in Python also, and we can provide additional functionality to the user. So yeah, that's all from my side actually. We can look into the questions.
Yeah, sure, Sumit. So before we proceed to answer your questions, I would like to request the attendees to please fill in the poll about feedback, as it helps us to conduct more such sessions. So you can check out, there is a feedback poll. Okay, so we can take the questions. Yeah. So will you read it out, or shall I read it to you, Sumit?
Sure, I can read out.
Yeah.
Rishabh.
Okay. Yeah. Because the attendees cannot see the questions. So before answering, it will be better if you read the
Sure,
question as well. Yeah.
sure,
Okay.
sure.
Please.
Sure. One question was, how do you get the NDVI data? Like, I assume it's interpolated data for cloud cover gap and satellite frequency. This was asked by Subhash. So this actually, we can compute it using the satellite images. So this could have been one of the pre-processing steps for our pipeline, but due to client confidentiality, the satellite images weren't shared with us. So this can be computed using the computer vision techniques. So this is also an interesting problem. We can discuss more offline on this. Coming to dynamic time warping in layman's terms, you can understand it like we have two subsequences, string 1 and string 2. So how much similar the string 1 is to the string 2? Like if we have hello world and if we have second string hello, so we have to convert it the hello world to hello. So this would give us the distance between the two strings, or the edit distance between the two strings. Either we can insert the characters or we can delete the characters. So hello, we can insert WOLRLD, and hello world, we can delete the characters WORLD. So this distance denotes the edit distance. So we are interested in the minimum cost when we are calculating the edit distance. So based on these operations, we are computing the DTW. So DTW is also similar to the uh, edit distance between the two strings. So how we can get the similarity between the two time sequences. how much the time one time signal is similar to the other time signal. I hope this resolves. Okay. This question, did you try regression on this problem? Okay, or we can discuss this question offline actually. I will require more details how the data is, if it's possible for you to share the data. I will type my email address in this chat. You can send me more details on this. Yeah, I can share the notebook with the DTW and ML models integration. It is in nascent stage actually. The code has to be refactored. Yes, that I think PPT and code mostly. I will share my email ID. This one is from anonymous attendee. Can you kindly reiterate the objectives? Like, can you clarify the question more? Rishabh, you can mail me the use case on my email ID. We can discuss further. Yeah, I have given a notebook walkthrough showing the DTW feature embedding and metric and integrating with ML models. Yeah. Yeah, Sumit, I will share the code book. Yeah, there is a question from Prashant. If two time series are somewhat similar, could there be a possibility of causality? Thanks. No, Prashant, actually. Here we are calculating the similarity between time series using a type of distance metric, not exactly a distance metric, because that metric doesn't fulfill all the properties of a distance or a norm in the Euclidean space. So mostly it will be negative. I will come more on this question. Yeah, Rishabh, over to you. Like,
Yeah,
there are no
yeah,
questions.
we have covered all the questions. Correct.
Yeah.
Okay. Do we have anything in the chat section? Okay. So, guys, I have shared the LinkedIn profile as well as his mail ID, so you can check it out and connect with him. So, thanks a lot, Sumit. On behalf of Analytics Vidhya, I would like to thank you for your time and delivering such a wonderful session. I am sure our audience found it insightful, and hopefully, we can conduct more such sessions with you in the future. Uh, the
Thank
LinkedIn
you, Rishabh.
profile is shared in the chat section, guys. You can check it out. Okay. So I hope you guys have filled in the feedback pool. If not, I request you to kindly fill it in. Uh, if you wish to conduct if you wish to conduct a webinar or facing any difficulty in registering for our upcoming sessions, please connect with us at editor@analyticsvidya.com. You'll find this in the chat section. Also, the recording of this session will be available on our YouTube channel. The link you will get in the chat section. And we'll be back with another session of the DataHour today itself. After half an hour, we have at 3 p.m. we have another session, and also we have 2 sessions tomorrow as well. So you can check that out on our website. The link for all these things are in the chat section. You can check. Thank you so much, Sumit,
Thank you.
for
Thank you,
being here.
Rishabh.
Yeah.
Thank you.
Yeah. Guys, the link is you can check it. Okay. Thank you so much, everyone.
Thank you.
So you guys can copy the link, whichever is required for you. Okay. I hope everyone has got it. Thanks a lot. Bye-bye.
Thank you, Rishabh. Bye.